Okay, we're here to take a look at section 12.6, the calculus of vector-valued functions. This is kind of where we've been headed from the beginning of this chapter. We started out defining vectors and exactly how the different operations worked. Then we talked about looking at vector-valued functions and curves in space. And now we're finally here to look at the calculus of vector-valued functions. The very nice thing is that this whole section can pretty much be summed up right here in the first sentence. Everything you learned about differentiating and integrating functions of the form y equals f of x carries over to vector-valued functions r of t. You can simply apply the rules of differentiation and integration to the individual components of r. Right, our r of t function has an x of t, y of t, z of t function, usually is the way that we think about it. And each one of those functions is a scalar function, meaning they're functions that live back in Calc 1. So everything that you did there basically works. So the majority of this section just breaks down to, see like questions 7 through 14 here, just derivative of vector valued functions, just take the derivative of each one of the component functions separately. And these are, it's just like doing 2 or 3 Calc 1 problems in one problem. Pretty similar for finding tangent vectors. You know how to find slope. There's a little bit of thinking to do there, but not too much. There's some examples in here you can look at for exactly how to go about doing that. Higher order derivatives. You want our double prime of t, our triple prime of t. You just keep taking higher order derivatives of the component parts, not a big deal. Integration, same thing. You might have to deal with kind of an initial condition though. But again, I think you can figure that out. Definite integrals, integrate each component and then evaluate according to the bounds on t, just like you would think. Actually, I think we're going to do this number 66 here. Integral from 0 to pi over 4 of secant squared ti minus 2 cosine tj minus k dt. And I've got this over here. Integral of secant squared is tangent. Integral of minus 2 cosine t is minus 2 sine t. And integral of minus 1 is minus t. Now you're evaluating from 0 to pi over 4. Tangent at pi over 4 is 1. 0 disappears. Sine at pi over 4 is root 2 over 2. But I've got negative 2 of those. So the 2's cancel. You just get negative root 2. And the 0 goes away. And pi over 4 evaluated at t is negative pi over 4, and the 0 goes away. So there is our number 66. Most of the problems that you're going to run into here are really just kind of that simple, just repeating Calc 1 processes over and over again. The way that you can make these more difficult is you could make the integrals of derivatives more difficult. So I say this is easy, but the concept is pretty easy. But of course, it can be as hard as we want to make the derivatives or the integrals. So there's that. Okay, let's go back and look at some of the definitions in the section. The derivative and tangent vectors. So if you've got a function, f of ti, g of tj, h of tk, and everything's differentiable on an interval, then you have a derivative, and you do it just like we said, take the f prime, g prime, h prime functions. As long as r prime of t is not 0, so it's not the 0 vector, then r prime of t is a tangent vector. It could also be called the velocity vector. This is position, its derivative is velocity at the corresponding point rt. So they might ask you to find tangent vectors. It's just the derivative r prime of t. If you want a unit tangent vector, you just take r prime of t divided by the magnitude of r prime of t, and we use this capital T of t for that. You will see that as we go on through the chapter. Another nice thing, theorem 12.7, pretty much all the rules that we want to work the way that we want them to work. So the derivative of a constant is 0. The derivative of a sum is the sum of the derivatives. The derivative of a product works kind of like we would want the product rule to work. Notice there's a lot of different kinds of products here. We've got a scalar function with a vector function, works like the regular product rule. Let me skip down to dot product. The dot product, again, works just like the product rule. The cross product works just like the product rule, okay? We're actually going to prove some of these in the exercises. I'm not going to do it now. Here's the chain rule. The derivative of a vector valued function, it's got a scalar function inside. Well, it's the derivative of the vector valued function times the derivative of the function on the inside. I'm pretty sure we all know that's how the chain rule works. Works the same way here. There is a proof of the chain rule here. It's a lot of symbol moving around. That one gets a little complicated. Also, my iCloud storage is almost full. You might want to look at this proof of the dot product rule. It's pretty simple. And when you have to prove some of these other ones, that might be a good one to come back and look at. The definition of an indefinite integral of a vector valued function. Notice that they use the capital letters when they integrate, capital F, capital G, capital H. Those are the antiderivatives. And the only thing to pay attention to here is that we're integrating with respect to t. We get capital R of t, and we have a c, and that c is an arbitrary constant vector. On some of the homework problems, you know what that c is because they tell you. So you have to use that fact.